The next keynote speaker is Prof. Shuyang from Tongji University. His topic of keynote is a physical and numerical modeling of boundary layer wind-induced load on structures. As we noticed that numbers of study now conducted using overcome the wind tunnel, but most of the study are not, the consideration before the study is very important. I think this topic has become more interesting. Just to little bit introduce, Prof. Shuyang is a professor in Tongji University. He is also Secretary General of International Association of Wind Engineers recently. Without further ado, I think, Prof, I think I give this floor to you. Thank you.
Thank you, Mr. Nom-san. It's my great pleasure to have a presentation at the ANC, the National Conference on Wind Engineering, Wind and Earthquake Engineering, and also ICC. Is it CE? I have to. Okay. So now I start my. Can you hear me now? You can hear me, is it? Okay. So now I'm starting my presentation. So actually, before the presentation, I discussed with Professor Nom-san. So actually now there are many people doing some start their study on wind engineering. So we choose this topic. It's some fundamental, not so advanced as Professor Damula just introduced, but I think it's fundamental. It's necessary for the beginners of the wind engineering. So here, at first, we introduce what we are the target of the flow we are considering for wind engineering. So here at the top of here, we show some climate that may introduce very strong wind. So you can find that we have monsoon and have a tropic cyclone, thunderstorm, tornadoes, everything where it's possible to make a strong wind and cause damage. But here, this topic will focus on the boundary layer wind flow. So mainly to what relates to monsoon, tropic cyclone is or some is that mainly related to the tropic cyclones. So here we have a terminology of synoptic or non-synoptic. So if you look at the wind climate, you find that the scale of the phenomenon become smaller from the left to the right. So when we talk on the synoptic wind, so usually it means extended pressure systems or front depressions and a stationary wind. For non-stationary wind, you can imagine that it's caused by a very strong convective phenomenon. So it's convective storm or downburst transient wind, localized windstorm, thunderstorm, tornado. So you can have different terminology to describe a non-synoptic wind. But for the most important case for us is typhoon. So whether typhoon is synoptic or non-synoptic. But I think many times ago when Professor Wickery has in his paper he defined that if we consider in terms of the wind speed characteristics, so the typhoon it can be considered as a synoptic, because if we look at the 10-minute mean statistics, it is still synoptic wind. But if we look at the wind speed magnitude in a typhoon process, it will increase, wind speed will changing or increase during typhoon process. So possibly people can consider it is non-synoptic wind, but it is in a very how to say very long time scale. So usually when we consider the 10-minute mean period, we can consider typhoon as a synoptic wind process also. So what is the difference between synoptic wind and a non-synoptic wind? So here you may notice that for synoptic wind, it has a velocity profile. So the wind speed will increase with height. But for the non-synoptic wind, you can see also from this figure, you can find that it increases very fast. It has a lower jet flow, but it will decrease with height. So it is an outflow accompany severe convective weather systems. So in currently most design code and all recommendations, we consider the synoptic wind Of course, we have some particular attention to long synoptic wind load for such as thunderstorm or typhoon or tornadoes. But usually we assume we consider a synoptic wind, even it's a part of a typhoon. So we need to simulate such synoptic wind flow in the wind tunnel. That's why the topic this topic will focus on the boundary layer wind flow. We will not consider tornado, downburst, such kind of very severe wind phenomena for the wind disasters. So what is atmosphere boundary flow? So here you can see at the up of this slide, we see a turbulent boundary layer developing. It's not on atmosphere boundary flow, but it's a boundary layer flow developing on a flat plate. It's a wind tunnel test visualization. You found that at the flow at the right side, left side, the flow is nominal, but after the flowing down to the right side, the flow becomes turbulent. So in up of the boundary layer, it is still nominal, but at the bottom of over the flat plate, it becomes turbulent. So it will generate a turbulent boundary layer. It is similar to our Earth. So here is a description of the velocity profile. It's also taken from Professor Tamara's lectures. So you may find that because they have some roughness blocks on the Earth, so we are living on roughness blocks. So you may find that it will generate velocity profile. The wind speed will increase with height to the height of, we call it gradient height, ZG. So over the beyond the over G, the flow will be a free wind, so velocity will be constant. But anyway, it will generate a velocity profile. So all the structures are standing in such kind of atmosphere boundary layer. So when we do a simulation in wind tunnel or numerical simulations, we have to consider such kind of the modeling of such kind of a turbulent boundary layer. So actually, Professor Davenport, we use Davenport chain to consider the process of wind resistant design of structures. So you may find that at the beginning, this chain, at first, we have to study on the wind climate. And after that, we have to decide the terrain effect. And after that, I'm sorry. Sorry, the hotel service comes, sorry. So after we decide the terrain effect, because the terrain, possibly your building will be in an open sea, in a coast area, or your building will be in an urban area, or some very high-rise building area. So it will have a different terrain category. So we have to consider terrain category. The third one is aerodynamic effect. We have to consider the impact of the wind on the structures. Also, after that, we have to consider dynamic effects. And these dynamic effects will become very dominant or very profit if the structure is very slender, such as a long-span bridge. So finally, we have a criteria. So actually, wind engineering is a combination of flow dynamics and structure dynamics. So following this Davenport chain, we will decide the wind load and response on the structures. But here, usually we have 4 approaches to study wind engineering. And the first is analytical method, and then wind tunnel test, of course, field measurement and numerical simulations. But this topic will consider the wind tunnel test and the numerical simulations. So in the wind tunnel test or numerical simulation, we have to considering modeling of atmosphere boundary layer and its interaction with the structures. After we got, if we get the some raw data from the wind tunnel test, we can do some analysis of the raw load and also do some further analysis for the design purpose. But anyway, at the first stage, we have to do wind tunnel test and the numerical simulations. So what in this 5 point of the Davenport chain? So what Professor Davenport initially considered and what we are doing now. So if you see, look at the first is the wind climate. So at the beginning of the initial concept of the Davenport chain, for wind climate, people will consider statistic model for wind speed and direction. So we have to consider rainy or single Weber distributions. And then we will analysis by extreme value analysis to get design wind speed for a longer return period. But currently, and actually not currently, possibly from 10 years, 20 years ago, people have done a lot of research of double Weber for mixed climate, considering monsoon and the typhoon. But even though currently, some people like Professor Sorani, he will consider the mixed climate of monsoon, typhoon, and thunderstorm is developing. And also currently we do a monocolor simulation of tropical cyclones to have a description of the typhoon wind speed. We made a lot of virtual typhoons. And even recently, people will do computer weather reconstruction method by WRF studies, because the meteorological person, they do a lot of WRF study to get to simulate the typhoon process. So everything now for wind climate is developing now. And for the second one is influence of terrain. So the initial concept, and then the time people consider surface drop for the Z0 for the wind velocity profile in logger law, and also alpha ZG of the power law index, and also gradient height of the ABL. So after that, even people will consider a more detailed description of the velocity profile with Harris-Davis profile for the entire planetary boundary layer. And also we will consider the homogeneous and the transition of terrains is also a topic, not current, and also influence of topography. For the aerodynamic effect, its initial concept considers cause-state force and pressure coefficient, the boundary layer wind tunnel test. So we will test local pressures, overall forces, and aeroelastic models. Of course, currently, it will be very common to test by high frequency force balance model for pressure, for the wind force measurement. And also for bridge person, we do taut street model for bridges. And also for both, we have to study instantaneous area load, instantaneous pattern load database for generic buildings. And I think this one becomes more possible now. People use AI to estimate the aerodynamic effect. And also now people are doing large scale testings. Now for the dynamic effect, so its initial concept considering, for instance, the size effect, linearization, and the frequency domain effect, peak wind effect, rigid structure. For rigid structure, we have this description, and for flexible structures, we have to combine the background and the resonant component. So currently, people will do more time frequency analysis and also multiple mode response and nonlinear structure actions. For the criteria, for the ultimate and serviceability limited state, it's an initial concept, but now, as Professor Tamara just introduced, people consider more on the comfort of occupant and also comfort of safety and pedestrians and fatigue damage. So a lot of new materials, new contents are included into the wind engineering, but we still have to do wind tunnel test or simulation to provide some raw first-hand data for further analysis. So here, I will go to entering the wind tunnel description of the wind tunnel test. Sorry, I don't have that. You see, as I introduced, we have to simulate the velocity profile in the wind tunnel. And this wind velocity profile changes with the terrain category. Here, right side is a very old figure. You see with the increase of roughness, so the velocity profile will become more slim, and it will generate a more larger power law index. So if you want to simulate the boundary layer. So we have to simulate this kind of flow profile in the wind tunnel. So right side, you can see as we use such kind of spires, the red one, and also the roughness blocks to develop such kind of turbulent boundary layer. So after we simulate such kind of a velocity profile and also turbulent intensity, we can test a lot of tests in the wind tunnel test. So here you may find that the turbulence simulation is a key issue for wind tunnel modeling. So when we modeling the atmosphere boundary layer in wind tunnel, we have at least we have to consider vertical profile of wind velocity. So such kind of category 1, 2, 3, 4, 5 is depending on the country. Some country has 5, some country has 6, and some country has just only 1 category. In addition to the velocity profile velocity, we have to consider turbulent intensity also, and the power spectrum and the coherence. We want to simulate more naturally the wind tunnel, the velocity turbulent boundary layer to test the wind load. Here is an example of the how the roughness blocks contribute to the turbulence generation. You see, if in a flat plate, we have a lot of roughness blocks. So if we compare between the velocity profile between without roughness block and with velocity profile blocks, you may find that the velocity it will generate different velocity profiles between with and without roughness blocks. And for the rough surface condition, it will have a very slim, much slim velocity profile than the smooth case. Is for this expression use power law. So usually for wind structure analysis, but for the environment study, usually people will consider the flow very close to the ground. So we use log law to estimate velocity, some dominant parameters like Z0 in the wind tunnel test for environment studies. And also we consider the Reynolds number and also the sigma U to simulate the roughness block will contribute to the simulation of to develop the turbulence. Another approach to generate turbulence is grid turbulence. Here is the example. So people will add a grid in the wind tunnel. It will generate isotropic turbulence, means IU equal to IV equal to IW. So we use such kind of a grid turbulence also can for another wind tunnel for other studies for the aerodynamic analysis. So in wind tunnel, at first we have to measure a lot of things like wind velocity, pressure, and force. Here just example of the measurement of velocity in wind tunnel. The most common one is a pitot tube. You can see here people have used tube to measure the velocity. But here we can measure the make point measurement. And what we measured is the mean velocity, mean component only. So this one, people also use hot wire or hot film to test the velocity. So if we have I type, we have only one component. If we know the dominant flow direction, we can make U component. So here, if we use X type, so we can measure 2 velocity component. Of course, if we have to know the dominant flow directions. Still, we also have 3D type. This hot wire, hot film can make higher frequency measurement, but still it is a point measurement, and this film have to be put inside the wind tunnel. This one is a Coppola probe. Coppola probe now is become very common in China. Some countries does not, especially in fluid mechanics laboratories, they don't want to use Coppola probe. But anyway, this Coppola probe is very robust. It will not break. For the wire, hot wire, it will break very easily. So actually, it is some expensive. But for this Coppola, it's very robust, and it can measure 3-dimensional velocity component. So we use it in a lot Coppola probe in our wind tunnel. And here also is a laser LDV, laser Doppler anemometer. Still, they use some Doppler shift to measure the velocity, but still it is a point measurement. Of course, this kind of case for laser, you use laser. So this sensor will not, it's not necessary to put the sensor inside the tunnel. It's different with the up 3 anemometers. Of course, currently people use PIV. It will be a very strong velocity measurement facility. So it will provide not only point measurement, it will provide in an area how the velocity is distributed in a velocity in an area. So we can use this velocity to validate our simulation result. Also here, we use pressure measurement. So for pressure measurement, we have a lot of pressure taps on the models, and then we can simultaneously measure the pressure on the models. Of course, because the pressure, the tap is linked transferred to the transducer by a tube. So we have to do some tubing effect analysis to compensate for. But we can now have a lot of channels measured together, in order to make sure in order the analysis is simultaneous velocity pressure. And here is a high frequency force balance test. So you can find that we can use node cells to measure the wind force on the structures. But here people have to attend to all the facility have a frequency response. So we have to, for this kind of high frequency force balance, we have to higher F0 is desired. So we have to use very lightweight models for the force balance measurement. But when we do wind tunnel test, of course, we have to consider similarity now, because we do a small scale model in the wind tunnel. So we have to consider geometrical similarity. A lot of geometrical similarity we have to consider. We have to consider the similarity of the building itself. And also we have to consider the geometric similarity between the air and the flow inside the wind tunnel. And also we have to consider approaching flow. I just introduced when we modeling approaching flow in the wind tunnel, we have to consider mean velocity profile, turbulent intensity, and power spectrum. And also a lot of dynamic similarities we have to consider. Otherwise, we cannot explain or we cannot extend our wind tunnel test to the real structures. If we want to extend your result into a real structure, you have to satisfy such kind of similarity laws as much as possible. But still, as Professor Pamela has said, for wind tunnel test, no matter how careful you have to do wind tunnel test, there are still some limitations. So we cannot reproduce the exact flow characteristics, because such as a turbulence scale is very difficult to be modeled in wind tunnel. And for the building model, because we use a more scaled model, for instance, for example, 1/400, or sometimes we have 1 to 1,000, a very small model. So you cannot model the very fine structure, fine textures of the buildings. So we cannot have exactly the same geometric shape. And also similarity laws, especially such as the Reynolds number, is very difficult to be satisfied. But anyway, we have to consider to satisfy such kind of requirement. But also we have to understand there are some limitations of wind tunnel test. Here's some practical issues. So for the Reynolds number is a very difficult problem, especially for curved surface. For if you study on a dome, so because the separation point will shift, so it's not stationary for separation point. So it will have a stronger Reynolds number effect. But if you have a cylinder, for a rectangular cylinder, so because the separation point is fixed already, so the Reynolds number also has effect on the attachment point. But anyway, the separation point is fixed. So possibly the Reynolds number effect is not so obvious as in the curved surfaces. So to solve this problem, so usually people in wind tunnel test, we use add some surface roughness on the model, try to simulate high Reynolds number flow phenomenon. Or you choose different wind tunnel, such as pressurized wind tunnel to have a high Reynolds number flow, Reynolds number simulations. And also we have to consider blockage rate effect. You cannot put a very big model inside your wind tunnel because it will changing the flow around the buildings. So usually we have a blockage effect. We consider the blockage ratio is smaller than 5%, or at least smaller than 10%. Here the blockage ratio, we have definitions. And others, we have to consider wall constraint effect and modeling of surrounding areas. Prof. Thomas just introduced. We have to model surrounding areas. And also we have to consider length scale and temporal scale, because we scaled down our model already. So the real 10-minute phenomenon in the wind tunnel in the scale is different. We have to consider the relation of length scale and the time scale. Of course, we have to pay attention to the reference pressures. Here, I will introduce just some examples. Prof. Thomas just showed that this is a wind tunnel test. So there's a necessity to model surrounding structures when you simulate the wind speed distribution and the wind load distributions. Still in wind tunnel test, we have an elastic model. Here it just shows a named mass model for wind tunnel test. We measure the wind force by high frequency force balance in the bottom of the buildings for this named mass model. And also people can use the elastic model. It's a rocking type. You can change the C, the damping ratio, and for changing K, you can some spring here, some oil here, to changing the dynamic parameters of the structure to do some high-rise building analysis. Here is some example for our bridge test. You can test here it shows the force balance, clear force balance to measure the wind force on a bridge deck model. Also, you can use it's a vibration. This one is a free vibration. You have springs. It's a free vibration test for a bridge deck, and we use the accelerated momenters to test it. Here also we can also do forced vibration test, and also we can do some measurement on the bridge deck. For bridge deck, the pressure measurement is not so common as in the building side, but still, in some cases, we have to do some pressure measurement for the bridge deck. Also for bridge analysis test, we have a tall strip model test. You have some tall wires to connect the deck sections. So it is just between the sectional model and the full elastic model. So we use this tall strip model test. So usually in wind tunnel for bridge test, we have a lot of tests on the displacement transducers, use laser transducer displacement and analysis, the force and the displacement. For bridge, we also do a lot of full area elastic model test. Here is just some a list we have to consider for the deck, for cable, for tower, for piers. We have a geometrical similarity. Of course, we have to satisfy, and we have considered stiffness and aerodynamic stiff similarities. We are quite complicated for a bridge side because the bridge is very sensitive and have a very small damping. It's very flexible to the structures. So for the bridge side, we also have here just some tower model test. We also do some even elastic model for the tower models, because now currently for the long span bridges, the tower of the building of the bridge enters to several hundred meters high. So it's just now very slender high-rise buildings. Another issue we do wind tunnel test is a cable for rain reduced vibration, wind vibration of a test of cables. So he found that we have a rain simulation devices. It have a spray to simulate the wind to rain, and then we have a spring, have a cable here, try to simulate the rain-induced vibration. Also, we have a vehicle bridge model test. Here you can some models. We do some models in wind tunnel. So for the next step Another approach is to simulate such kind of wind phenomenon is by CFD. So here just also describe briefly the wind CFD. So CFD basically is a commercial approach, is a numerical approach to simulate predict phenomena of quantities of the flow by solving equations of motion and flow at a discrete set point. So it has a lot of wide applications already. So, but before you use the CFD approach to simulate for wind engine simulation, so we can see at first the flow chart. So for have a real flow phenomenon, I mean the real flow structure interactions. Usually at first you have to generate governing equations. And these governing equations, usually people think it is Navier-Stokes equations, but before that, we have to use some approximations. And you have to add some turbulence model or multiple phase model, some models to fit your problem. And after that, you can generate the governing equations. So everything dependent, the starting point. If you use, for instance, you have got turbulence model, you use Round's model, you use ALS model. So you will have different governing equations. Of course, the beginning is Navier-Stokes equation. So after you get the governing equations, you will consider the scheme. Possibly you use FDM, FEM, FVM, or discrete vortex method. So here you have discretized these your domain, or if you don't use grid, possibly it becomes easier. But anyway, after that, you have to solve the equations. The solve this equation is common for everybody, for dynamic structure, for structure analysis, for the fluid analysis. To solve this question is almost similar. The problem is that you have to choose a appropriate model to generate governing equations, and you have to decide the numerical approach to solve your equations. Of course, for CFD, we have to do a lot of validations to make sure your result is acceptable. But for wind engineering, so we have to consider the problem is that we have a very severe black body aerodynamics. As the wind tunnel test showing that it has different scale. These three videos shows the vortex changing with the turbulence intensity of the incoming flow. So if the incoming flow is turbulent, you can find that it's nominal turbulent is nominal incoming flow. This one is no turbulent intensity, is a higher turbulent intensity flow. So you can find that the general flow structure possibly is similar to each other, but with adding of turbulence, the flow structure will become more fine. So we have to consider such a kind of black body aerodynamics and a turbulence effect. It's possible for the wake turbulence or the incoming atmosphere boundary layer turbulence. And we also, for us, we have wind engineering, we have a very complicated body shape. And also we have multiple scale phenomena. And another problem is we have a very high Reynolds number of the real flow. So here just the governing equations of the fluid. So now I don't want to describe it, but the problem, you have to understand that the problem comes from the advection term. It's non-linear, it's very difficult to solve. For the diffusion term, it will stabilize your calculation. So actually, we want to add more diffusion term effect into our calculation, so we can make our calculation become stable. But this kind of behavior is just like adding more damping into your system. So of course, with more damping, your structure will vibration less, but it's not real phenomena. So here for CFD is the same. If you want to make your calculation become stable, you can possibly choose some numerical approach to add some diffusion term effect, but it's not good. It's just like adding pressure, adding a damping, increased damping ratio. Here's just like a example. For the high Reynolds number, because I introduced our Reynolds number very high. So what we do, usually we have two approaches. The first one is we use upwind scheme. Here it shows the performance of upwind scheme. If we have an initial real phenomenon of this type of velocity fluctuation, if you use upwind scheme, so with time advancing, you can find that this curve become more curved. The calculation will become more stable, but it's not. It will cause errors in our simulation, especially when you want to evaluate the maximum value of your calculation. The mean value possibly is maintained, but for the instantaneous value, it was changed. So in addition to the upwind scheme, we consider as a numerical technique to stabilize the calculation. So in addition to the upwind scheme, people will use turbulence model. So turbulence model is expected to solve high Reynolds number flow because they are developed according to the physical character of the flow. Usually, now currently, we have runs, Reynolds number, Reynolds average Levi-Stokes runs, and another one is large eddy simulation. These two widely adopt numerical turbulence models for engineering applications. And if you want, but here people will consider which one is better. So for the practical issues, we don't want to use upwind scheme. We want to solve the problem by adding turbulence model only. But the problem is even you have a very strong computer, with only turbulence model, you still cannot solve the high Reynolds number conditions. So usually we combine these two together. So, but we want to combine these two upwind and a turbulence model together, use this scheme to resolve the advection term. But here, so we have an alpha parameter. So we want, if the alpha is 0, it will become a central difference scheme. So we use the turbulence viscosity turbulence model only. But if we put alpha equal to 1, it will be an upwind scheme. As I introduced, we don't actually, although we don't want to add alpha into our calculation. But the problem is, if without this alpha or without this damping, our calculation cannot go in, it will stop. So we have to add this kind of add a smaller damping into our calculation, try to see whether our calculation can go ahead. If your calculation can go ahead, so we use a small or 0 alpha. But if you find your calculation cannot go ahead, so sometimes we have to add a large alpha. So this scheme will become an upwind scheme, just like introducing more dampings into the calculation. So comparing between runs and LES. So runs average turbulence over time. It solves a lot of several turbulence status equations to estimate the turbulence effect. It's a very efficient method if you want to know the mean and IM value only. So especially for the wind environment evaluations, if people considering the pedestrian wind speed, but they consider the mean wind speed only. So runs is a very strong tool to get a result. It's not so accurate as the LES, but people usually accept the result of runs. I think it's 10 years ago. And now recently, the environment person, they also have a tendency to adopt LES for the mean wind speed calculations. But for runs, so his formulation is complicated. They have a lot of parameters to be assumed. So you have to assume a lot of values for a lot of parameters. But for LES, so every turbulence over space, it solves large scale component directly with a small scale component model. So it's a very easy to make an equation to get to estimate the turbulence viscosity. And very few parameters to be decided. The problems, it is very time consuming. But now currently the computer becomes very, very strong than before. I think even a small scale workstation can do several million grid calculations. So that's why people, even environment person, they want to do LES calculation, because the LES study calculation is really not so time consuming than previously. Here is just describe what's the difference between LES and runs, where the errors from. So if you see, look, the X is a wave number and the Y is energy spectrum. So if you say for DNS, we have to solve a quite range of a spectrum. But for rounds, it looks at the largest structure component only. So ALES is just between rounds and a DNS. So it's not so expensive as in DNS, but ALES will provide much better result than the rounds result if you look at the frequency domain phenomena. So most common widely used smart ALS model is smart model and the dynamic smart model. I think the common most utilized one is smart model. It is based on the assumption of local equilibrium between turbulence production and dissipation. So we use these calculations to get a mu e. But if you look at the assumption, so this assumption is based on a equivalent between a turbulence production and dissipation. That means that if you want to do ALES study, you have to cut the wave number to this range. So but usually people cannot. A lot of person, or a majority of the researchers, we have to do ALES at a lower wave number. Possibly we cannot afford to do a calculation close to DNS. So usually we cut our wave number to here and here and here. Of course, it's still higher than rounds, but usually people cannot cut to this equivalent. If you have an equivalent region, you have to do here. You have to cut off your high frequency at a very high frequency. And after this smugness model, we usually have to get a damping function into the viscosity models. Try to make sure you have a no slip boundary condition at the your calculation. But the key point is that for ALES study, the largest scale structure is solved directly. We do some modeling on the subgrid scale, but anyway, the grid scale is solved. So it's possible it's not necessary to consider such kind of parameters like CS or A+. It's not so meaningful. So we can, because the grid scale is solved directly. But here for CFD, we have a grid generation. We have to pay attention to. The truncation error decreases and the accuracy of simulation increases with increase in grid number. But the problems, if you use more grid number, you use more memory, you have more calculation work and more calculation time. So we have to pay attention to the grid generations. A good grid system must be able to get reliable results, be able to arrive at a stable calculation, have less useless grid. So when we do grid, people have to consider the oscillations of the grid, and the size ratio of the neighboring grid means the expanding ratio and the smoothness of the grid. And we have to put a lot of grid to resolve the boundary layer near the body. It's a problem possibly, particularly we have, because we are a wall boundary layer. Here are some examples of grid is O type for a cylinder. If you do a cylinder, and if for a rectangular cylinder, you have to make sure you see this grid curved near the surface. Try to make sure it is a 90 degree. So, but of course you cannot maintain. It's really 90 degree. But anyway, we have to put our effort to make the approach to 90 degree as possible. And also for building groups, it's a curvature coordinate. We have to put more grid near the body surface, and also have to curve the grid. And for this one is auto mesh. So we use grid is a Cartesian grid outside of the buildings, but near the buildings we have to use curved body fitted curves, and have to some area set of them area try to connect these two areas. So we have to make auto mesh to generate a grid system. Or for bridge, Usually we use unstructured grid because bridge deck is quite complicated. And in some cases, we use a virtual grid. There's no grid to for the body surface, but we use virtual grid to try to simulate the flow around a square cylinder. But actually, we didn't add a grid at the boundary at the body surface. Another problem is inflow turbulence generations, because as we introduced, we are talking on the turbulence. So without turbulence, you see it's a flow over here. So it will the flow separated and reattached and generated a wave. If we consider a nominal inflow, but for the atmospheric flow, it has turbulent. But and this turbulent will interact with the separated shear layer. So you can find that if turbulence comes, it will cut the separated shear layer and changing the velocity flow, the flow past here significantly. You see a very narrow dead water region in turbulence conditions. So also, numerical wind tunnel, we have to produce the turbulence also. So for turbulence, we have also two approaches. One is a stochastic method. We use some random procedures to generate inflow turbulence. Another way is for CFD simulations. You simulate a turbulent boundary layer by your numerical approach. So that means that, or you just simulate a physical wind tunnel. For instance, for a wind tunnel, as introduced, we use spires, reference blocks to generate the inflow turbulence. So also it's a physical wind tunnel, because we currently the computer become very powerful. So it's possible to simulate this physical wind tunnel by numerical approach. So we can get a turbulence velocity profile and a turbulence intensity by the numerical approaches. Also, still, I'll just introduce some result, because for inflow, laminar flow, for topography, for here, for laminar flow, the phenomenon, if you have turbulent flow, different wave will be generated here for the steep here, for the low here, and if the here have reference blocks. Such kind of phenomenon, especially for the complex topography, it's very difficult to be modeled in wind tunnel, because you need a very large round turntable. You need a big wind tunnel, but such a kind of thing is very easily to be generated in numerically. Also for the strong wind in urban area. So here this one is for Marina, and this one is inside our Tongji campus. So we can do such kind of we can modeling at first the buildings, put the buildings into your numerical domain, and then you simulate the flow around the building, and also of course the wind force on the structures it is possible. We do such kind of simulations. And for low-rise building and a high-rise building, we can simulate the flow and also the wind force by the numerical simulation. And also for some vibrating case, if you do some fundamental study, is for a rectangular cylinder, and also for the bridge, we can do such kind of analysis with some safety technique to simulate the flow and the force. And this is for the bridge deck. So we have this grid. We simulate the CD, CL, CM at different attack angle. We provide such kind of a 3-component wind force of bridge deck. And then also for the vibration case, we have to do Flutter analysis. So we have to, by Flutter derivatives of bridge deck, we also can simulate to get this kind of parameters by the wind tunnel test. Also, some wind test is very difficult to be done in wind physically, but we can simulate. Here is a water-air coupling process. Finally, I introduce that. So because it's a CFD, so we have to validate our data. There are a lot of data for fundamental researches. Also, actually, in our wind engineering field, you can do some validation by comparing with the data provided by a wind engineering person. I think first you can consider TTU field data. In Texas Tech, university, they have a they have a rectangular, have a building, low-rise building, measure field data, so we can measure, do some validations. And also AIJ, Architecture Institute of Japan, they have some not in both environmental and structure side, they have such kind of data provide, so we can to validate our calculation with the data. And also for the TPU data, Professor Tamura just introduced, they have a lot of database it's open, disclosed to the public. So we can go to their website and check the to evaluate our numerical simulation results. Okay, so finally, because I introduced both experiment and CFD. So when we compare these two, so we will see some difference between them. So if we look at the model, at first, the wind tunnel, usually we have a scaled model. Our building is very small. Building model is small in the wind tunnel test. But for CFD, if you use some commercial software, possibly you will add some scaled length. But usually it is dimensionless. So here CFD is stronger than experiment, because in experiment you have a scaled model as introduced. If you use a scaled model, sometimes it's very difficult to simulate the texture of the buildings, especially for instance, roughness around the buildings is almost impossible. And so for the applicability, so experiment is very restricted. In wind tunnel, you cannot assume a very high wind velocity, but for CFD, it's flexible. You can assume a condition that is very difficult to be modeled by the wind tunnel test. But the problem is that for the phenomenon, for the experiment, it is real phenomenon. We can see it with our eye. But for CFD, it's a virtual one. So the problem is here. But for the technology, for experiment, for wind tunnel test, is developed already. But for CFD, I think it is still developing, because in majority of the CFD person in wind engineering field, we just utilize some commercial software or some open source software. So here is a problem. If you don't develop a software by yourself, sometimes it's very difficult to understand the phenomenon behind. So I have to say that CFD is still in the developing process. So it will generate a problem of reliability. So people will consider experiment is high, but will consider CFD is not high. Because for CFD, if you're changing the inflow condition, or if you're changing some parameters, different person will have different result. But actually, this phenomenon is same as in experiment. Different wind tunnel is impossible to generate identical result from different wind tunnels. It's the same in CFD, but the problems, I think the problem CFD is a virtual one. So people will believe in experiment data. They always have questions on CFD. So under this situation, all national wind node code standards are formulated under the premise that wind nodes are simulated in wind tunnels. So here is the problem. So whether you do wind engineering research by wind tunnel test or numerical study, you have to consider by yourself. Have to choose one. Okay, thank you very much for your attention.
Okay, Prof. Thank you very much for your kind address, which is, I think we like to applause you for very good presentations. We would like to open a question to the floor. If we have a live question, you may unmute your mic and give a question online. Before that, just introduce yourself. I will try to allow one or two questions, a live question from this online. Okay, if not, I will read some question in here. Morning, Prof. I'm Atika from Islamic University, Malaysia. Okay. I'm doing wind tunnel testing on the overhang roof.
Yeah.
How can I install the pitot tube at the overhang since we have a very minimum upper and lower sides? It is possible to get only upper side. Can I get this? And is it we can only just assuming the value for the lower sides, or vice versa? Can you give a comment, bro?
I think this question is for wind tunnel test for hand roof, because if you want to simulate this part only, because it's very small. So the problem, I think, if you use a very small, for limited area, you model the limited area in the wind tunnel, so you cannot simulate wind coming flow profile. So I think this is a problem. So I think usually what we do is that at first you have to simulate the wind velocity profile, and then you put an integrated model, everything, the roof, the building, the roof, and your particular structure together in the wind tunnel. Of course, it will be a very small wind model, I believe. At first, you have to get these evaluations. After that, if you care the roof structure, some particular part, particularly at some locations, you have pick up some section to do wind tunnel test. Possibly it is allowed, but at first you have to put the whole structure as an integrated one in the wind tunnel and simulate it. Okay.
Okay, I have another written question here. Good morning, Prof. I'm your student from Tongji University.
Really?
I'm Jaya Singh. Jaya Singh.
Oh, okay.
I'm requesting to please show a slide again which have influence of terrain, explain its initial concept and current concept. He requests to review again about the influence of terrains. Yeah.
Means at the beginning of.
Yeah, in the beginning, I think, in the beginning, influence of terrain and its initial concept. Mr. Jaya Singh, if you you can also unmute your mic, Mr. Jaya Singh.
Yes. Miss Jaya Singh, yeah.
Miss Jaya Singh, sorry.
Yeah. Is this one?
Miss Jaya Singh, can you respond? You can unmute your mic and give us some explanation to Prof. Yeah. He's mentioned, yes, this slide. Yeah, this slide. Yeah, correct. Okay, any other questions from the floors, from the participants? I have one question, Prof. We will, every time we will asking when CFD will take over wind tunnel. every time. I think last 15 years, also same question, I think, same question.
Yes.
But still until now is still not yet been fully CFD because some of limitation. We understood the limitation. Can we in conducting in wind engineering, can we doing some hybrids, doing a combination of CFD and wind tunnel? Is it will be give a better result? What's your comment, bro?
I completely agree with you. But so CFD strong as somewhere and wind tunnel test as strong as somewhere. They have possibly we can use their advantages, combine the advantages to provide a more better resolutions for our design. I think for now currently, people always consider, just as you weighing of CFD will take over of wind tunnel test. The example is that in AIJ, Professor Tamura's country, Japan, at least they said the wind load can be obtained by wind tunnel test or CFD. So that means they admit, they accept the result of CFD already. It's a big improvement. I think other countries still does not accept CFD result for structure purpose. For environment studies, CFD is widely utilized. So I think CFD will have a very strong, very good future. I believe.
Okay, thank you for your comments. We have still a few minutes time. Any question, Prof?
May I add a comment?
Yeah, Prof. Tamura, please.
On Japanese situation. So as Professor Cao said, AIJ, Architecture Institute of Japan, we have published some recommendation on the wind load evaluation. In that document, they allow the CFD application for evaluation of wind load and wind pressure. But a very limited condition we can do this. And also maybe in that situation, wind tunnel test may be easier than CFD. But this is just a recommendation from academic field. And by law in Japan, the building standard law of Japan, we have for building construction and design. In that building law, we do not allow, not yet, but they are preparing some document to accept some part of wind load evaluation. We can use CFD, especially topographic effect and so forth. They tend to use the CFD, but fully, if you use CFD for wind load evaluation, they cannot accept the current situation. But the future, maybe, as Professor Cao said, the future trend is to accept CFD, but very strict condition is given to do this.
Thank you for your extra explanation, Prof. Any other participants like to have? We have still 1 or 2 minutes. We still have any questions? Okay, they have another question from Indonesia. Indonesia again. Dear, good morning, Prof. Cao. I think I'm Manza, researcher from Indonesia Aerodynamic Laboratory. I think he's also the previous TPU members, I think. I noticed him. How to tuning velocity profile at wind tunnel after we design spire and roughness, and we did not get the velocity profile target and turbulent profile also. You get the question, bro?
I think this question is how to simulate
tuning velocity profile. Yeah.
If I try and error.
I try and error. Okay.
Yeah. Okay. So that's why I think CFD is better than wind tunnel test, especially for this kind of design. So if we want to generate the velocity profile, you do possibly be tuning the spires, reference blocks. But so usually the wind tunnel, we will prepare. So this setting is for category A, this setting is for category B, this setting is for category 3. We try a lot of tests by try and error test, and then fix the combination of spire and reference blocks to generate turbulent, to generate the inflow. So it cannot fit. If you ask them to generate, for instance, alpha equal 0, 1.3, or even especially for some number, it's quite difficult to simulate the turbulent inflow, especially near the ground. very difficult, I think. But it's trial by error test, I think.
Okay. And any other questions? If not, I think maybe we can have a written question or email to directly to Prof. Chow.
Okay.
I think. Yeah. Yes, thank you very much, Prof. Chow. I think I know he's away from his office, but he's still committed today. I hope that maybe you can join us back in Malaysia after the pandemic is over.
Okay, thank you very much.
Okay, okay. We finished the keynote session number 2 now, and we will be according to the time we'll have a breaks for 5 minutes. I think maybe Prof. Tasya may share the PowerPoint first, and before we may start after this, for a while we have a breaks for secretary and for another 10 minutes, and we will start at 11:30 Malaysia time, GMT +8. We break for a while. Okay, 11:30 we may start again for keynote session 3.
Okay, thank you.
Thank you, Prof. Okay.